A light rope on a cylinder and a pulley. In figure, the cylinder and pulley turn without friction about stationary horizontal axes that pass through their centers. A light rope is wrapped around the cylinder, passes over the pulley, and has a 3 kilogram box suspended from its free end. There is no slipping between the rope and the pulley surface. The uniform cylinder has mass 5 kilograms and radius 40 centimeters. The pulley is a uniform disc with mass 2 kilograms and radius 20 centimeters. The box is released from rest and descends as the rope unwraps from the cylinder. Find the speed of the box when it has fallen 2.5 meters. Okay, so if we look at the potential energy of the box, so let's start with the potential energy. The potential energy U will have an initial value mgh. So this will be equal to, because it's a 3 kilogram box, 3 times 9.8, and it's falling 2.5 meters. So it's 2.5 meters above the ground initially. So that is 73.5 joules. And the final potential energy obviously will be 0 joules. It will be at the bottom. Now, if we concentrate on the kinetic energy, for the kinetic energy term, K, we have an initial value of 0 joules because it's released from rest, and final kinetic energy will be due to the rotation of the cylinder, rotation of the pulley, and the final translational kinetic energy of the box. So we will have three terms here: 1 over 2 I cylinder omega cylinder square plus 1 over 2 I pulley omega pulley square plus 1 over 2 mv final square, the final translational kinetic energy of the box. And we have this relationship between the final speed of the box and omega's. Final speed of the box will be related to omega cylinder, omega times radius of the cylinder. And it will be also related to the angular speed of the pulley, omega pulley times radius of the pulley. So we can write the final kinetic energy as 1 over 2 I cylinder V final square over R cylinder square plus 1 over 2 I pulley V final squared over R pulley squared plus 1 over 2 m V final squared. Okay, so let's concentrate on the uniform cylinder here. If we are at a distance r from the center, you can see that we will have a region in space where we have a small volume that is defined by dr, r d theta, and dh here. So this will be dh. Okay, so with that, if this is a uniform cylinder, we can write the mass density as the mass density rho will be the total mass of the cylinder, capital M, divided by pi r cylinder square times h, the volume of the cylinder. And if we look at, if this is our z-axis, then we can call this not dh, but maybe we should call it dz. So this is dz. Then we can write the volume of the differential element as r dr d theta dz. So this differential element will have a mass dm, which is equal to rho dv, which is the mass of the cylinder. So this is the mass of the cylinder divided by pi r cylinder square times h, the mass density, multiplied with the volume r dr d theta dz. Okay. Now, for rotations about the center of mass, we can write I center of mass is equal to rho integral z will go from 0 to h. The radial distance will go from 0 to r cylinder, and the angle will go from 0 to pi. So we have r square r dr d theta dz. So as you can see, I have taken rho m over pi r square h outside of the integral. So this gives us, if we perform the integrations one by one, for the r integral, r cubed dr will give us r to 4 over 4, r to 4 over 4. This is evaluated between r cylinder and 0, so this will be r cylinder to 4 over 4. The angle integral d theta will give us 2 pi times 2 pi minus 0. The dz integral will give us h. So this will be equal to you can see here we have this 4 becoming 2, so we get rid of this 2. Pi h rho divided by 2 multiplied with r cylinder to the 4th power. So for a rotation axis that goes through the center of mass, I center of mass will be equal to pi h divided by 2 multiplied with our rho m cylinder divided by pi r cylinder square h multiplied with r cylinder to the 4th power, and this will become a square basically, and we also get rid of the h's, and we will be left with, also the pi's will cancel, and we will be left with mass of the cylinder r cylinder square over 2. So mass of the cylinder r cylinder square over 2. This will be, if we substitute the numbers here, the mass of the cylinder is 5 kilograms and radius is 20 centimeters, 40 centimeters. So we have mass of the cylinder 5 times radius 0.4 meters square divided by 2. This will give us 0.4 kilograms meter square for the cylinder. Now we can concentrate on the uniform disk, which is our pulley, the uniform disk was done in problem 9.53. So we just recall the result from problem 9.53. I center of mass was 1 over 2 mass of the disk multiplied by radius of the disk square. So if we plug in the numbers, it will be 1 over 2 times what was the mass of the pulley, 2 kilograms, and radius was 20 centimeters. So this is 1 over 2 times 2, 0.2 square. So this becomes 0.04 kilograms meter square. So we can write now the final kinetic energy as 1 over 2 I cylinder omega cylinder square. This is 1 over 2 times I cylinder 0.4 kilograms per meter square we found here, multiplied with V final square divided by R cylinder square, which is 0.4 square. That's the first term. Second term is our 1 over 2 I pulley omega pulley square, rotational kinetic energy of the pulley, 1 over 2 times 0.04 times V final square over the radius of the pulley, 0.2 square, plus the translational kinetic energy 1 over 2, 3 kilograms times V final square. So this gives us 1.25 plus 0.5 plus 1.5 V final square, which is 3.25 V final square. Now, if you look at the change in mechanical energy of the system, delta E mechanical, which is change in kinetic energy plus change in potential energy, this should be equal to 0 because all the axes were frictionless. So the axles had no friction, so we have conservation of energy. So we find that delta K must be equal to minus delta U. So we can write 3.25 V final square must be equal to 73.5 joules, the change minus the change in potential energy, which gives us, for the final answer, V final should be 4.76 meters per second. Okay, now to summarize, we have a setup here that is consisting of a cylindrical a cylinder that has a string wrapped around it and a uniform disc pulley, and there's a box attached to the system which is released from rest and descends as the rope unwraps from the cylinder and goes over the pulley. So the cylinder and the pulley will rotate as the box will come down, and their angular speeds will increase, and the potential energy of the box will be turned into kinetic energy of the box and the rotational kinetic energies of the pulley and the cylinder. So that's the basic idea. And because these rotation axes are all going through the center of mass, we can write I center of mass for cylinder and the box, and there is no friction in the system, so they can turn without friction about stationary horizontal axles that pass through their centers. Okay, so the initial potential energy is mgh for the box, where m is the mass of the box, h is the initial height, which is 2.5 meters. Final potential energy is 0. The kinetic energy initial value is 0 because it was released from rest. Final kinetic energy is rotational kinetic energy of the cylinder, 1/2 I cylinder omega cylinder square plus rotational kinetic energy of the pulley, 1/2 I pulley omega pulley square plus 1/2 mv final square. And there is a relationship between the speed of the box and the angular speeds of the pulley and the cylinder. Omega cylinder times R cylinder equals omega pulley times R pulley equals the final speed of the box. Actually, this relationship is correct throughout the motion, but for the final situation, this is also correct. So what I'm calling omega cylinder is the final angular speed of the cylinder, and likewise for the pulley. And for the uniform cylinder, we write the uniform mass density, capital M divided by pi r square h. We notice that if we concentrate on a mass element here, it has a volume dr dz r d theta, the arc length. So by performing the integral throughout the volume of the cylinder, we find it's mr squared over 2. And we also had the same result, mr squared over 2, for the uniform disk from problem 9.53. So we substitute the masses and the radii corresponding to the cylinder and the pulley, and we calculate the final kinetic energy by plugging in the numbers and set it equal to minus the change in potential energy, because there is conservation of energy due to the condition of having no friction in the system. So conservation of energy applies. Therefore, we can use this equality, delta k is equal to minus delta u, and solve for the final speed.